It's my honor to introduce our next speaker, Professor Pibernik. And Richard is going to talk from small to large data, how we can leverage synthetic data for machine learning. Richard is the full professor of logistics and quantitative methods at the University of Würzburg in Germany. He heads a research group. And Richard, I should say that, in German, he has a chair of a department, and we were trying to figure out how do we translate that in the US, as we don't have that here. It's very German, yeah. So here we've said he heads a research group dedicated to data-driven operations and supply chain management. Richard is also an adjunct professor at the Zaragoza Logistics Center and a visiting professor at the Malaysia Institute for Supply Chain Innovation. Both institutions are part of MIT's Global Scale Network. Richard has brought a variety of his students and his research group with him, and all of them also have posters, which we're going to visit later this afternoon. Richard, all yours. Thank you.
Well, thank you very much, Jan. Thank you. So, yes, you see, well, thank you for having us. You see there are quite a number of people here. Jan explained it. We have, for our standards, a pretty big group of researchers dedicated to machine learning in supply chain management and operations. Over there, and this presentation is joint work. We have multiple projects, research projects, also with companies. And we thought maybe today it's nicer to not just pick one of these paper projects, but to share some of our joint insights. We've been working on this for 3, 4, 5 years, and explain our vision. It's work in progress, what I'm showing you. It's early work, but I think it connects nicely to what we heard this morning from Joran already, and from Barrett. Is he still there? Sorry. I'm sorry, with the mask, it makes it very difficult. So I think it'll connect nicely to what we heard this morning. And I want to start actually, so the topic is, how can we leverage synthetic data? Barrett, you brought up the term synthetic data, and that we don't have enough data actually to train sophisticated machine learning models. That's exactly what I'm going to talk about. So how can we leverage synthetic data for machine learning in supply chain management and operations? But before I hop into this, I want to go a similar route as Joran, right? You see these general applications. The old deep blue AlphaGo, AlphaZero, autonomous driving. And I want to look at basically their data strategies and their methods, because I believe this can tell us something for supply chain management, for operations management. Remember Deep Blue, that was still brute force computing. They had real data from experts, and they essentially did enumeration and evaluation on real historical chess games. With brute force computing. And then, so that was basically heuristics, and they used some optimization techniques for the end game. And then, as Joran said, the breakthrough was AlphaGo. I'm not going to explain all of this again. But what do? They trained 2 reinforcement learning agents, only told them the rules of the game. They played against each other. They had no real data. They had no real data. It was only self-play. It was only synthetic data. So they played this very often. They created a lot of synthetic data. And essentially, that's how they got this breakthrough that Joran already described. And the interesting thing is, with AlphaZero, they said, we can not only do this for Go, we can do this for a broader class of problems, all kinds of board games. We can do this with chess. So what did they do? AlphaZero got chess champion, beat the stockfish, the then champion, with much less computational resources. They can play shogi and so on. So essentially a smart way to generate data, to train an agent, and to apply that to a bigger class of problems. And that's already what Joran said. I think this could be very interesting to us. And we are going in a similar direction there. Now, if you look at autonomous driving, where the state space, so these were indications of the state spaces of the problems. They use, and this is interesting, they use real data, of course. yeah, from their test drivers, from their cars, and so on. But then they feed this into a simulation model, and they create more synthetic data. So they have a mixed strategy. Why? Yeah, because they can, through that, they can also simulate rare events that don't really happen even in their real data. Yeah? So they have this mixed strategy. So, and this is also something that we're trying to do, to pursue a mixed strategy of synthetic data and real data. So can we not do, so hang on, I want to mention this. So what they do is essentially they solve complex problems, data-driven, end-to-end. I'm going to explain that, automated, and they have smart ways to generate data. And I think this is something that should be part of the vision also for machine learning in supply chain management, operations management. Yeah? So can we not do something similar in operations management? Let me show you a little bit what we did. So we mainly, well, here we go. We mainly work in, let me do it like this, inventory control, capacity management, yeah, network routing. So very traditional OM problems that are fairly repetitive that we all know. We work with, these are some of our company partners, yeah. In each research project, we have at least one company partner. We get real data. So it's always data-driven. That's true. That's definitely true. End-to-end means we take the company data and we directly derive some decision, some prescription. Yeah, I'm going to explain that in a second. So our approaches that we developed are pretty much end-to-end with some little restriction and some minor doubts. But can we automate? And that's what we cannot do. Because what are we doing? We're basically creating for each problem here a tailored solution. Yeah, and that's what I think this is where we maybe are going wrong. This is what the OM community has been doing the last 30 years. For every tiny little inventory problem, yeah, with a certain parametric distribution, we found a specific tailored algorithm, yeah, to solve that problem. But that doesn't scale. That cannot be automated. Yeah? And I see that we are, and I'm talking about myself, right? I'm not talking about you, me and my group. We're doing the same thing again. We're building really cool machine learning models, yeah, but very specific, very much tailored, and they don't scale well. Yeah, let me show you one example. So this is from a paper that we recently published. This is data from a logistics company from a sorting operation. Very boring, right? They sort parcels and stuff like that. They have 3 sorting lines. Yeah, you see this up here. Oh, sorry. Nico, this is the same device as you have, and it always gets me crazy, right? Yeah, I know. I'm just getting too old for these gadgets, right? So they have 3 service lines. Yeah, one is fully automated, one is semi-automated, one is manual. They sort all kinds of different packages. Yeah, and they have to staff these service lines, and they want to staff them for next week. Yeah, they want to decide today how many people do I need in which line next week. Yeah, and there is some substitution, some upgrading going on. I can move the people around from one line to another. That's what the data looks like. Yeah, if you look at the data, this is the demand data over 4 years, daily demand for the different service lines. It's non-stationary. Yeah, it's heteroscedastic. So what we see is that the coefficient of variation varies over time. Yeah, and of course there are correlations, and the correlations are not constant over time. Yeah, so the demand for the different service lines are sometimes positively correlated, sometimes negatively. Yeah, so that's our data essentially, our demand data, and we believe we can explain this through some features clearly. Yeah, so for example, which day is that? Which day of the week, day of the month, day of the year? Yeah, are there holidays, lag demand features? Yeah, so these may be predictive of the demand. Yeah, so these are our features. So we have, on the one hand, demand, and imagine this as a data table where in the first column I have demand observations for 4 years. Yeah, and in the next couple of columns I have all of these features. Here we have like 150 features. So that's our data table. Yeah, and the rows are the sample size n. That's, if you look at this, 1,000. Yeah, roughly 4 years. But that's not true, because we're taking weekly decisions, we really only have 200 relevant observations. 200 observations, 150 features, pretty high dimensional. We're going to run into problems. Yeah? Good, so that's what it looks like. And we assume, so this will be important, that the data and the features, they are jointly distributed. Yeah? And remember this will always be the joint distribution in the following. So we have a joint distribution, but we don't know that distribution. Yeah? But that table that I just described is basically sampled IID from that distribution. Okay? So that's what we're assuming. And these are reasonable, basically reasonable assumptions. So we're going to take that table, and we may have much more data. Yeah? And we learn, we have a prescriptive model. Sorry, with this mask, this is killing me. We have a prescriptive model where we basically learn from the data directly some output. That's what we call end-to-end. Yeah? No distributional assumptions, no human interventions, no in-between steps, but we have some function that takes as input the data and outputs the capacities for the next week for the different service lines. Okay? So that's the end-to-end part. And how do we do this typically? What methods do we use? I'm going to do this quickly, but I need it a little bit later. We have two classes of methods. The one is, you know that, you probably all know that, is empirical risk minimization based regression. So we're trying to find a function, Q. Now that's a vector in our capacity case, right? Because we have multiple service lines. So I'm trying to find a function from a function space that minimizes the empirical loss over my data sample, over my n samples. Yeah? So this is the loss. And the loss is, for example, a cost or a gap to some optimal profit. Yeah? So now this can be a simple function space, a linear function space. Then we have something like a linear regression. But that can also be defined by something complex, by a deep neural network, right? By some tree-based method, some gradient boosting we heard before. That could be defining my function space, and I'm looking for this Q. But now you already probably are thinking, wow, if that's a complex function space and we only have 200 observations and we have 150 features, that's not going to work well. So we either overfit or we have to regularize a lot, so we're losing a lot of information from the features. Yeah? So we'll get back to this. What's the alternative that we can do? And this is something that Bertsimas and Kalos basically proposed. I'm just introducing it here because we're going to use it later on. It's called, or we call it, weighted sample average approximation. So they look not at the joint distribution. Let me try again. Not at the joint distribution, but on the conditional distribution of D, given some x, some vector. Yeah? So what are they doing? They're basically saying, I'm looking for the Q that minimizes some weighted loss, and that weight comes from some machine learning approach. The weight measures the similarity between, for example, a feature for next week with all other features in the past, right? And then we optimize against these weights. Yeah? So that's a slightly different approach. So these two classes, they are data-driven, they're end-to-end, but they're highly problem-specific. That's what I said before. We have to define these functions here for every problem and how we solve it, right? We have to do the same thing here. We have to define the weights. And that gets very tedious, a lot of work, a lot of tuning, cross-validation, engineering, and so on. So it doesn't scale well, yeah? Good. But the nice thing is, for these approaches that I just showed you, we have some nice analytical properties or theoretical properties, at least if we take n to infinity. Yeah? So Bertsimas and Kalos showed that their approach is asymptotically optimal, at least for some of their weight functions. So it converges as n goes to infinity. It converges to the full information optimum. We showed something similar for our capacity problem for a kernelized approach, just in a continuous function space. We can develop performance bounds. So we can do all this in the limiting case. But, so there's more to do. This is not exhaustive, right? I mean, there's much more we can do theoretically. But this has no practical relevance. Yeah? Because usually we have samples which are much smaller, as I described before. Yeah? And the convergence is, we can show that also theoretically, the convergence is slow. Yeah, the more features we have, yeah, the longer, the more samples we need. Oh, it's, sorry. I have to, no, it's not wrong, right? Sorry. No, that's what I had, right? Well, anyway, sorry. I apologize. It's first time in 2 years, I still have to get used back to it, right? So convergence is bad. So the more features I have, the more samples I need. And unfortunately, that's not a linear relationship, but it has an unfavorable nonlinear relationship. Yeah? The performance bounds are very loose, yeah? For small sample sizes. They don't tell us anything. Yeah? And so I borrowed this chart here to highlight this from Bertzimas and Kallos. They did a small stylized experiments with 3 features. Remember, we have 150, something like this. Yeah? And they showed convergence of their approaches. And we really get convergence in 10 to the power of 4. So at, say, 10,000 observations for 3 features. So we're not there. Yeah? We're somewhere over here. And over here, we cannot say anything about which method will work well. Yeah? We have no means, at least theoretically, to prove that some method will perform better than another method. Yeah? And if you look at this, we even see this for the news vendor, for our simple news vendor model. So these are some results that we got for 4 different data sets on which we applied different machine learning news vendor models. Look, Larry, I'm sorry, this one is yours. Yeah? No, but it works well. Sorry, I have to do this joke. It works well on other data sets. But what do we see? Yeah? So these are 4 data sets. 2 are our own, kind of we collected them. 2 are publicly available, yeah, from Kaggle. What do we see? We don't have a dominant model. Yeah? There is no real structure in this. We cannot say that one method outperforms the other. It's highly dependent on the data set for small data. Yeah? And of course, this is just a news vendor. That's not what we really want to solve, Joran. Yeah? I mean, if you had done all of your stuff on the news vendor, your life would have been much easier. Yeah? That's not what we want to solve. So it's also highly problem specific and gets more complicated. So this is just a side note. Maybe you're interested in this. So inspired by the machine learning community, we developed, or our researchers, Andreas and Simone, who is here, they developed a package, an open source Python package, yeah, in which we included our data sets, a whole number of data sets, and we implemented all these methods for testing purposes. Yeah, you can use that. You can put on your own data. You can put on in your own methods, yeah, for testing. It's still the news vendor. But we also use this for educational purposes. We built a whole course around this. Yeah, we have Colab notebooks, which are really nice, and tutorials and videos. And we use that to teach students, yeah, understand how machine learning and supply chain and data-driven stuff works. So if you're interested, we're happy to share all the material that we have. Yeah, you can basically have a look at the repository and so on. Good. This being said, so yes, data-driven end-to-end, but it's not very automated. And automation will probably come through deep reinforcement learning, as Joran had pointed out. But the problem is deep reinforcement learning is much more data hungry, yeah, than our other methods that I showed you. Yeah? So how can we deal with this? And this is kind of our vision that I want to show you. So we want to create this pipeline, yeah, which is data-driven, end-to-end, and automated, where we have as input real data, and then we have a synthetic data model that essentially generates a lot of synthetic data out of our real data. Yeah? I'll explain this in a second how this works. And then we use this big data that we generated from our real data to pre-train an agent. Yeah, so that's a pre-trained agent on synthetic data. And then we will use the real data again to fine-tune that agent. Yeah? So that's our idea of our pipeline, and we want to automate this for a big class of problem instances. So let's say for all type of, or many different types of inventory problems or capacity problems. Yeah? So now here you see, oh, it's gone again. Huh? So here you see different methods for synthetic data generation. Of course. So this is kind of in ascending order of complexity and sophistication. So distribution fitting and sampling is the easiest one. Yeah? So from our data table, we then just take the first column, fit the distribution, and sample from this. I believe, Joran, this is what mainly you have been doing. I don't want to criticize you. I know what you did and admire what you did. But we basically don't want to do this because it doesn't include the features. It doesn't include the X's, yeah, these 150 features. So we would like to sample from this joint unknown distribution. We want to learn this joint distribution, the X by D distribution, yeah, to also use the features. And for this, we did something foolish. We used the most complicated data generation model, generative adversarial networks, and combined it with the most complicated machine learning model and applied it to some multi-period inventory model. And I don't know who of you remembers the Hitchhiker's Guide to the Galaxy, yeah, Larry? So what did we get as a result? Exactly, right? 42. So we couldn't interpret it. So we stepped back and we said, let's make this easier, right? We still use the generative adversarial networks, but we built an easier evaluation framework, which I quickly want to show you. So this is how these GANs work. This is how we generate synthetic data. So we basically have two networks that play a minimax game. This guy over here, the generator, he generates synthetic samples and wants to make them look like they're real data samples. And this guy over here tries to distinguish them. Yeah, and tries to say, no, this is not real, this is synthetic. Yeah, and they play this game, and in equilibrium, yeah, we get the best solution for generating this synthetic data. So we're essentially learning this unknown distribution X by G. That's the idea. Yeah. We have some problems here. The training, it's expensive, yeah, computationally expensive. Training is unstable. Simone here has a poster on this if you're interested in the technical details. Yeah. The loss function is no indicator of the quality. So we have to determine. So now imagine I sampled 50,000. Now I have a data table of 50,000 D and X's, yeah, rows. And now I have to find out how good does that approximate the underlying distribution, which I don't know. Yeah, that's not so easy. So we have a little trick. Yeah, we first try to evaluate the quality, and we said, let's just feed this synthetic data into a simple operations model to convert it into cost. Let's just feed it into a news vendor model and benchmark it. So first we said, let's take our data table, the D, the real data, fit the distribution, get the news vendor quantile, and plot the total costs on the test set. Here, lower is better, right? So then we get this. Yeah? This is just for distribution fitting, for the simplest way to generate synthetic data. Then we took our GAN data, yeah, our, say, 50,000 observations that we generated synthetically, and we applied weighted SAA, which I showed you before, on that GAN data. And then we plot the curve. And we see, oh, we're doing better than distribution fitting. And the difference between the two, that's kind of the value of the features. That's the value of information. Yeah, because I have these X's in my data table and not just sampling from the D's. Yeah? So, but now you ask probably, what happens if we apply the same weighted SAA on the real data? And that's a little bit disappointing, yeah? Because on the real data, it does better. So the difference between these two you can interpret as that's our synthetic data error. Yeah? So that's our synthetic data error. That's what we're losing. Now the question is, now remember, this is still the news vendor. This is not, I mean, Joran correctly said reinforcement learning, and that is best applied or has its biggest potential in some stochastic multi-period setting. Now we're still looking at this easy news vendor because it's still tractable. We still understand what's going on. But now the question is, can we somehow get this blue curve close to this orange curve or even below? Yeah, that's what we're trying to do. And now our strategy is to say, if we have so much data, then we can do reinforcement learning. We're using, am I running late? We're losing performance, yeah, or we can gain performance by using a better model, which does not have to regularize so much, yeah. That's our first, so we have a different model, and we want to do this fine-tuning that I mentioned before, yeah. And now I can show you the results for this. So this was just the evaluation. Now we want to put the two things together. Yeah, so now we want to bring in the deep reinforcement learning and the fine-tuning. And let me show you some results. So these, hang on, I didn't mention this. These results here, this was real data from our bakery. Yeah, I know, I mean, it's real data, yeah, and we have a lot of that. So in some products, and now we're just picking one product, and you may be saying, oh, they're cherry picking. Yeah, they tried thousands of products until they found one where it works well, but that's actually not the case. But we have to be careful. We cannot generalize yet. Yeah, so I want to qualify this. So what you see here is essentially the performance. So now we have normalized profit. So higher is better. Yeah. For weighted SAA, that's the Bertsimmers and Kallos approach, on the real data. That's the green one. The gray one is reinforcement learning on our synthetic data, yeah, that we generated with our GAN. Then the blue one is reinforcement learning on the small data, the real data. And the last one, this is our model that we first train on the synthetic data and then fine-tune with the real data. And now you see that essentially this is outperforming all other methods across different service levels, yeah, in this example. Now let me try to give you some intuition on what is going on the right-hand side. So this is a little bit complicated, yeah. So this is the demand data. Here, this gray line that you see here, that's the demand data in our test set. Yeah, so the models have not seen that data. Sorted in ascending order, just to give it some more structure. Yeah? So we have lowest demand here, lowest demand is here, and highest demand is there. And this is the solution here, this horizontal line, the solution that we would get if we did weighted SAA. We just optimized over the sample without weighting. Sorry, it's SAA, not weighted SAA. Yeah, we just optimize over the sample without weighting. So we have 70% below of realizations, 30% above. And that makes sense because we have a 70% service level. Yeah? So now let's look at what happens in this green method. So now we have weighted SAA, yeah, the Bertsimmers and Kallos method. And what you see now are the orders, the corresponding orders. These are the dots. And you see, so most of the orders are in this band here. And then it seems like we have some binary feature, yeah, like a weekday, that kind of increases these orders. And it looks pretty okay, yeah, but it's kind of a step change, yeah. So this step change may come from strong regularization, or there are simply no other features that contain a lot of value, yeah. So that we don't really know, yeah. So now let's look at what happens with our reinforcement learning on the purely synthetic data. Whoops. On the purely synthetic data. So what do we see? it always underorders. So that doesn't seem to work well. So it underorders, and that, however, we looked at the distribution. So if you look at this, the light gray is the real data, and the light blue is our GAN distribution, yeah, our synthetic distribution. It's smoother, but it's somewhat shifted to the left. Yeah, so that's the error, our synthetic data error. So it's shifted to the left. Yeah, and that's also why we underorder here. So that's not nice. Yeah. So if we do now you see the blue dots now, the dark blue dots are the same model, but on the real data. And here what we see is it overorders. And our hypothesis is it overorders because it cannot learn the safety buffer in the news vendor model. And you see this here as well. Yeah, at 50%, so here we have, at 50% we have no safety buffer, right? At 50% it works pretty well, but it gets worse and worse the higher my service level. Yeah, the more important my, my safety buffer gets. So it cannot learn the safety buffer. It does not have enough observations to learn this. It can learn the pattern, the demand pattern pretty nicely. Yeah, so that structure is nice, but not the safety buffer. So now what we can do is we do our fine-tuned model. You know, you see it kind of lies in between the two. So what happens there? Our fine-tuned model uses all the synthetic data, and it learns from the synthetic data, it learns the safety buffer. Yeah? And from the real data, it learns that it should not underorder. Yeah? So we combine both the synthetic data, and it gives us value, and the real data, which also gives us value. And that's the idea here. And that works pretty well in this instance. Yeah? That makes sense? Yeah? Did I forget anything? No? Good. So now if we want to generalize this, of course, we somehow have to find out, so this was just one instance, we somehow have to find out how can we measure this, and what do we really want to find out? And if you look at this, if my synthetic generation process was perfect, so I would approximate perfectly this unknown distribution, then I would have some theoretical optimum. Yeah? I mean, then I can easily apply any method. We know, we have seen that for n to infinity, we converge to the full information optimum. But now we have some error. I showed you this error. Yeah? And now the question is, if we only do real data, how big is the error then? We can get worse because of overfitting or too strong regularization, but we may get better. And now the question is, if we combine the synthetic and the real data, you remember, like the Tesla guys, yeah, in this mixed strategy, yeah, we will definitely not get worse, but we can probably close some of that gap. That's what I was trying to show you. But we have no clue how we can quantify that gap at this point. That's our big problem. Yeah? So we have more questions than answers. Yeah? And of course, how can we generalize this? That's what I just mentioned. What is the right synthetic data generation strategy? Yeah, how much weight do I put on the synthetic data? Yeah, and on the real data in the fine-tuning? Yeah, so what's the right learning strategy? So this we have not resolved yet. Yeah, but it already looks promising. Yeah, in a very simple setting. Now, of course, the scientific issues. Some of you may have been thinking that for a while already. How are we ever going to get this published? Yeah, because we simply are not, at least I have no means, we have no means to get rigorous results, theoretical results in terms of convergence properties, in terms of performance bounds for this, let me call it a monster, right? I mean, we have multiple neural networks that we use in this approach, and it gets very, very difficult to show anything. Yeah, so right now what we can do is we can do extensive testing. Yeah, build a big framework, make it open source, put many data sets in there and see how it works. But obviously, for the academic community, this is, at least for some journals, not enough and not enough theory. So that's what we're struggling with, but we believe that this may be the future, at least in practice. Okay, thank you very much.
So when I saw you go from synthetic to real data, I'd actually been thinking of doing exactly the opposite. That is, starting with the real data and then adding the synthetic. And I'm wondering if you tested that and what, or why you kind of went in the direction that you did in this approach.
Let me ask you, why would you turn it around? What's the rationale?
So my thinking was that you would sort of, you have the real data, and then you sort of learn on that, and you have a few observations that are sort of seeding it. And then with the synthetic data, you're getting more robust because you have more observations. Well, we haven't tried this. I think the main reason for us was that we observed this synthetic data error, right? I mean, we're not, at this point, we're not able to perfectly learn this unknown distribution. Yeah, we don't even know what perfect means for a distribution that we don't know, right? So we saw that error, and our rationale was to correct that error. So if we turn this around, my worry would be to say, well, we use some real data, and then we basically introduce that synthetic error, right? And we don't converge closer to a better solution, but we make it worse again. But I think we have just also not tried it yet. I would have to think a little bit more. Yeah, I don't know what you guys think, if you have something to add on, but it's worth a thought. That was just our rationale. Yeah, okay.
Some kind of pre-training for the model, like in the imaging community, and then try to specialize the model on our particular data set. So maybe if we have another demand data set from a similar company, maybe even pre-training on the old data would help to learn some structures that weekends are important, seasons are important, and stuff like that. But to be honest, we did not try your approach, so maybe it just works better. I have no idea. We can both try.
Let me get the microphone to speed up things.
Thanks a lot. I like the fact that you publish the data sets open access and everything. But shouldn't we be publishing like ground truth data sets where we have all these relationships, and then we can sample from that? Because then at least for comparative reasons, you would be able to capture your synthetic error, right?
True, but. I mean, we always have this discussion. Should we just build a simulation model and simulate from different distributions or impose some relationships? But, I just feel that it always ends up in some kind of reverse engineering. Yeah, I mean, Cynthia Rudin said it's good to use synthetic data where we have ground truth. I understand. But to really get a meaningful data set with like 150 features and complex relationship, and I think that's what we want to learn. I think that gets a very arbitrary model, and you learn effects that you induced yourself, yeah, and you're training a model onto something that you created yourself, and see how good does my model learn my imposed randomness and noise. I'm skeptical about this, yeah, and then. So we take it to a small scale, yeah, and then we do like with 2 or 3 features, and we say, yeah, can our model learn this for 2 or 3 features? And we see, yes, it can, and then everybody says, yeah, but that's pretty easy, yeah, that's not realistic. Yeah, so it's kind of, it doesn't really make it more publishable, I believe, or it makes it not easier to publish, and I'm a little bit, to tell you the truth, I'm a bit fed up of making up data, yeah. I just find it more interesting to use real data and to live with all of the problems that are associated with this. Yeah.
There is a question is that how is this method be different from the adversarial data augmentation in DL? And he or she also want to double check, is the data you simulate mimicking the real world data or synthetic data that you have ground truth with?
So, I'm not sure I got it. Were these two questions or was that one question?
Yes, this is.
So let me do the second one. Does that,
Okay.
what was that, mimic the
The real world data or synthetic data that you have ground truth with.
Exactly. We're using the real data and we're trying to infer its unknown distribution with the covariates. Yeah, that's all. It is exclusively, our synthetic data is exclusively built on the real data and this learning process of the data generating model, yeah, the underlying data generating process. So now you have to ask the first question again.
Yeah, the fourth question is, how is this method be different from the adversarial data augmentation in DL?
Hang on, Simone. Let's get a microphone first.
So I hope I understood the question right, but basically we're using the same architectures that people in deep learning and machine learning use for generating these images that everybody knows, like the people that never existed, etc. But
okay, now I got the question.
our models are specialized for tabular data, so there are some architectures that fit to tabular data, and we just use those.
Sorry, maybe we can add that maybe we can add that we think that we have a slight advantage over the imaging community because for them it's very hard to evaluate how good is my gun. So they can show you the images and you can say, okay, it looks like a person, but it's pretty hard to write a number on it. And in our case, we can just evaluate the costs made for a decision on this data. And if we can make good decisions on this data, for our means, the gun learned well.
Yeah, we don't. I mean, if the decisions are good, then the data generating process for us is good. Yeah. Okay. So you see, this is very convenient. Yeah. If you bring all of your people, you get less embarrassed. Yeah. Thank you, Nico, Simone. Any more questions? To whom do I return this? Thank you. Sarah.
Thank you.
So, thank you very much.
All right, we'll take a 15-minute break until 3 o'clock.